Let us start. Remember, we have finished the ideal Bose gas problem. Now we are doing ideal Fermi gas. And up to now, I have derived the general properties of ideal Fermi gas. Now, what I have done up to now was valid for all temperatures in terms of Fermi-Dirac functions. So you can have two limits, a high temperature limit and low temperature limit. What I am going to do now is to introduce, mention Sommerfeld's approximation. Which is valid at very low temperatures, at low temperatures only. And you can read about it in Appendix E in your book. This makes life quite easy at this limit. So you can derive whatever you like by using this very handy approximation. Remember, let us define a new variable by ln of fugacity, which is beta mu, temperature dependent quantity. This approximation is exactly like this one, an integral from 0 to x by x dx e to the x minus c plus 1. This is the Fermi-Dirac distribution function times a function whose integral is taken, is, in this approximation, 0 to c phi x dx plus calculated at x equals c plus 7 pi 4 plus higher order terms. Well, this is kind of a transform form. A better form can be written in this form, in this way. Anything multiplying the Fermi-Dirac distribution function integrated from 0 to infinity can be approximated by We usually cut off this expansion at the second term, so we don't go to the fourth order term in temperature. Very easy, isn't it? You have any function multiplying the Fermi-Dirac distribution function, and all the complexity is coming from Fermi-Dirac distribution function. You get rid of it. There is no distribution function on the right-hand side, and use only the function multiplying it and its derivatives to write the result of the integral. It's quite an easy thing to do, as I'm going to show you. Now, what are these thermodynamic quantities at low temperatures? I have done this. Low temperatures, where I can use this approximation. I have already done that and gave you all the results, but let me do it this way, this easy way. Instead of dealing with the functions, Fermi-Dirac functions, let's use Sommerfels approximation. For example, if you want to take the average number of particles in your system with negligible fluctuation in equilibrium, we can write this as an integral like this, isn't it? Well, this is density of states, number of states you are going to fill with particles, fermions. This is the Fermi-Dirac distribution function, average occupation number. So by multiplying this with the occupation number, you only count the particles in the occupied states, because that thing will be zero if the state is unoccupied, and that will not contribute to the number of particles, isn't it? So you only count the occupied levels, and that will give you the number of fermions in the problem, in your system. This is, again, Fermi-Dirac distribution function, which is e to the beta e minus mu plus 1, or 1 over z inverse e to the beta e plus 1. Z is e to the beta mu minus sign, it is z to the minus 1. Okay? Now, let's try to calculate certain quantities. Low temperatures, there is one absolute limit, which is T equals 0 limit. At T equals 0, everything becomes very simple, isn't it? At 0 temperatures, you don't have any corrections or contributions. You only have the first term. This is an important limit. Let's do a calculation at 0K for the fermions. For example, average energy is Well, now I have to integrate from 0 to Fermi energy. Why? Instead of going to infinity, they are empty. Everything above Fermi energy is empty. Energy and density of states. Okay? That, well, why don't I have this factor? I have to have that, isn't it? Energy times the density of states times the Fermi-Dirac. Why don't I have that? Because it is 1 up to EF, isn't it? So it must be n bar E, but that is equal to 1. Divided by the number of particles. So I am taking the average value of energy per particle. So that becomes very easy. Integrals are easy because that drops down. The temperature dependence is not included in this limit. Let's do it here. That is equal to, well, in 3 dimensions, we know that this is a constant times square root of energy, isn't it? 3D. 2D constant, and in 1D it is inversely proportional. You have to know those density of state forms. So this is E 3 hours D divided by E 1/2 D. So that gives you, well, very simple, 2 over 5 EF 5 over 2 divided by 2 over 3 EF 3 over 2. That is 3 over 5 EF. So average energy per particle then is 3 over 5 EF. This is energy per particle. If you have n particles, n fermions in your system, this gives you a total which is E 3 over 5 NEF, isn't it? So this factor is nothing but total number of particles. If you sum over density of states, you get the total number of particles. So energy divided by total number of particles is energy per particle. You have to multiply it with the number of particles you have. So that's a very easy calculation. Now, this proves that the highest occupied energy level, Fermi energy, is representing chemical potential at this limit, isn't it? So everything is very easy at 0K, no corrections. Now, using the approximation, let's include the corrections, temperature-dependent terms. Let's calculate them and see if we are going to get the same results we got with our better treatment. Here is the average number of particles. I replace it with the number of particles in the system, fluctuations being small, equilibrium. So it is 0 to infinity, d density of states, bar E. Now I have to include the Fermi-Dirac distribution function. Is this okay for everybody? Can you follow me? Okay. So that is density of states. This is Fermi-Dirac distribution function. I'm just counting the full occupied states. That should give me the number of particles in my system. Now, this we know can be written as follows with the approximation. That expression gives us the following. From 0 to mu, dE rho E plus first correction was this term, isn't it? I omit the third order correction, get the first correction that is proportional to t squared. This is the approximation I gave you, isn't it? Well, in my derivation, early derivation, I gave you terms up to t squared, isn't it? That's why I am doing it up to this. You can try the fourth order if you like. Okay. Let's calculate this. Well, the function here, multiplying Fermi-Dirac, is just the density of states. That's why I keep the density of states. Phi is the density of states here in the approximation, isn't it? If I calculate energy, of course, that function multiplying Fermi-Dirac was E times rho E. So my phi will be E times rho E in that case, isn't it? Huh? Depending on what you are calculating, that function phi in the approximation changes. Now, let's write this, separate this as two parts, one from 0 to Fermi energy EF at t equals 0, dE rho E, plus apart from EF to mu, dE rho E, isn't it? We can always do that. Well, if we do that, we are really looking at the limit as t goes to 0, and in this limit, of course, the chemical potential goes to Fermi energy. Eh? So, in this limit, then I can write the expression as follows. Well, let's look at this. Since n equals 0 to EF in this limit, dE rho E, that is the total number of particles, isn't it? This part, Huh? So that thing will cancel it. Huh? So we end up with a relation between this and that correction term. And let's write that. So approximately we have mu, well, let's write what we have. EF mu dE rho E is given by minus I have that, isn't it? With the change in sign, of course, because the sum is equal to 0. Now, this is a small term, and keeping that the value at Fermi energy, I can write this approximately as mu minus EF times rho EF. Taking the density of states at the Fermi energy, take it out, and that's it. And that must be minus pi squared over 6. So I'm trying to get the first order corrections, if you like, using the approximation. This term is quite small, isn't it? We are at very low temperatures. We have a very small difference. So when this is small, then I can approximate this as to be calculated at E equals EF instead of mu. I'm very close to that value. If I do that, here is what I get. So this is kind of an example of actual calculations using the Sommerfeld approximation. This gives us mu as EF minus pi squared over 6 kB T squared rho prime calculated at Fermi energy and rho calculated Fermi energy. So density of states and its derivative comes in. So what happens, we have derived, but chemical potential becomes smaller than its value at T equals 0. Yeah. It reduces. There's a negative sign here. That's first observation, important observation. Now, let's calculate this for free electrons, fermions, in 3 dimensions. You can do it in 2 and 1 dimensions. You know the form of density of states. In this 3 dimension, density of states is this is mass and K type of terms included in this constant. Is proportional to square root of energy. So derivative is 1/2 C 1 over square root of E, isn't it? When you take the derivative, 1/2 minus 1 minus 1/2. Very simple. So we have an explicit temperature dependence at very low temperatures of the chemical potential then. So This gives us a result, well, with those approximations, EF minus pi squared over 6 kb t squared 1 over 2 EF. Okay. When you calculate this at E equals EF, you have to put these expressions as, okay, square root EF, 1 over square root EF, EF goes up, gives you an EF. Okay, that's the result. Or you can also write this as follows. If you take it to EF parentheses, 1 minus pi squared over 12. Well, I told you, you can write that as KBTF, huh? In terms of temperature, T over TF squared. That's the first correction. Do you remember this result? This is exactly as before, the result we found by using a full calculation. So I gave you a very simple calculation. I think you can do a little bit more complicated energy calculation. Let's do that. You should fill in the steps if you like. Energy, average energy or internal energy can be written as, again, I divide the first term into 2, 0 to EF, dE phi E. Phi E now is E times rho E, that's those states, isn't it? You are taking average of energy. What is the average of energy? Well, average energy is, you take the energy, multiply it density of states, multiply Fermi-Dirac distribution function, and integrate. Now you can take it from 0 to infinity simply because if in this range particles occupy up to chemical potential, then that thing will be 0 above the highest energy occupied level. So this tells you which one of these are occupied, so you can count only the contribution from occupied states. Is that okay? So instead of writing this, I am using the approximation. So in this expression, that is my function multiplying Fermi-Dirac distribution function. So anything multiplying Fermi-Dirac distribution function is the function in the approximation. So this is the two parts. So the actual form of this is an integral from 0 to mu of dE phi. Dividing it into 2, you get this expression. And the first correction, as always, squared. Okay, this first correction can be written as rho at mu plus mu times rho prime at mu. apply the approximation. Okay, go back to the approximation and see how you are going to do it. Please do it. So, I will leave the steps to you, but let me show you the important part. Well, you can write this as constant 2/5 5/2. The first integral is easy, this part, from 0 to EF, the t equals 0 part, plus from EF to mu, d rho e times e phi plus pi squared over 6 as we have done before. You can write this approximately as mu minus EF rho EF times EF, Fermi energy. Exactly the same step as we have done before without the energy term. And here you can replace mu by EF, Fermi energy. So I'm going to very low temperatures, in other words. If you do this, I will leave the steps to you. You can get the following. Finally, 3/5 and EF plus 6 kBT squared rho EF. That's what you get. Okay. Remember, I'm using the fact that in 3 dimensions, this is a constant times square root energy. So, if you use this, well, that thing then stays at the Fermi level, can be related to EF expression. So the result can be written as 3/5 NEF 1 plus 512 T over TF squared. This is also exactly as before. So you get the energy expression at low temperatures. Do you recall this? Remember this expression? Huh? Not exactly, but you should be familiar with it. Go back to your notes and you'll see. Finally, you can also do the pressure term. See, this way of doing things is extremely easy, isn't it? Compared with what we have done before, it becomes simplified. Finally, the pressure Well, since we have calculated energy, just divide it by volume. So that is 2 over 5 EF over volume per particle. This is V over N. One plus 5 pi squared over 12 T over TF squared. Up to that approximation, we got exactly the same result as before. Okay? So that's what I wanted to show you. You can still discuss the physics of these, how the various thermodynamic quantities change as temperature increases at very low temperatures, and the corrections always, first order correction comes as T squared. Okay? Since T is small, that term altogether is small, isn't it? So any expansion should go to terms smaller and smaller. If T squared is small, T to the fourth is even much smaller, isn't it? So, very easy way to do it. So, what I advise you is to learn the technique and apply it if you are not able to continue with the full formalism. Huh? Do you have any questions? Anything to ask about this approximation? So you have to remember at least the first order correction. Okay, you have to be able to write down the approximation up to first order. The other part, T to the 4 part, can be included if necessary. Okay? Any questions again? Okay then, let's stop here and discuss the results for your exam.